So honestly, first I want to say I feel a bit flattered to be invited to this workshop because I'm really an NLP person. This is not really my area of expertise. So when I told a few of my colleagues in the last few days that I'm speaking at this workshop, they were even surprised I actually work on AI safety topics. So for this talk, I would like to really give all the credit of this talk's content to a group of very talented Princeton graduate students that I list here, only list a few of them here, who are actually really passionate about doing research in AI safety. And I've been very lucky to collaborate and work with some of the students over the past year. Some of them are my students, some of them actually, most of them are even not my students. So it's very likely that I even don't know many of the kind of recent work in this space, but I will do my best to discuss some of the amazing work they have done. And I'm also looking forward to learning more about the research presented as a workshop today. So also I would like to quickly mention this kind of new initiative at Princeton. So basically, this is also a student-led effort called Princeton AI Alignment and Safety Seminar, led by the students, also Zadika. So they basically already invited many scholars in this community to really talk about many alignment and safety-related topics. So if you're interested in these talks, feel free to check out, or if you are interested in being involved, feel free to reach out to. Okay, so in this talk, I will discuss two types of vulnerabilities of large language models, or like AI models, text-to-image models. So we all know that today these models or AI models have to go through extensive safety fine-tuning or alignment process before the model release. So this to make sure these models to become actually helpful and also harmless. So I want to talk about two types of vulnerabilities. So first, these models are actually taught to basically like what Andy just talked about. So to not generate harmful content. For example, if we write a tutorial on how to make a bomb in ChatGPT, the model will refuse such requests. And the second type of the vulnerability I want to talk about is actually to teach the model how to not generate copyright content. So if I put a instruction like give me an image of Mario in GPT-4o, today the model will basically say I'm unable to create an image of the Mario due to the copyright restrictions. So it's actually not able to generate this image for you. But in the later part of this talk, I will tell you that it's actually pretty easy to bypass this alignment. You can still generate an image like this. So there are actually a lot of research questions we can think about in this space. So Andy already talked a lot about all these different questions. So from a text, how easy it is actually for us to break the current aligned language models. For the defense, how should we actually address all this or mitigate these vulnerabilities? And I also want to say there are also important research question in the middle that is actually, I think, is still not fully addressed in how should we do the evaluation. So how should we really systematically evaluate all these models and also compare the different attacks and the mitigations? So I'm trying to cover all of this a little bit in this talk. So I will start with talking about the basically different types of jailbreaks people have been doing for breaking these models in generating unsafe content. So Andy already spoke before me, so I don't really need to introduce this kind of the adversarial suffix attack. So the GCG attack is basically essentially a way of doing this kind of gradient-based discrete optimization that you can actually find a discrete suffix that you can actually prepend to the harmful instruction, so that actually you can bypass the basic safety alignment. So the most interesting thing here is these adversarial prompts that you can actually transfer from the open source models to the closed source models, such as like from Vicuna to ChatGPT or Claude. So there's another type of the attack called a fine-tuning attack. So Xiangyu is a PhD student at Princeton. So he had this super cool work basically showing that you can actually bypass the safety alignment by just fine-tuning the model on 100 harmful instructions. So this can be done basically very easily with open source models. But you can also do this actually with closed source models, with ChatGPT that has some kind of fine-tuning API. So as a result, you can see on the right here. So the first column here, the first two charts on the left, here is basically you fine-tune on like 100 harmful examples. So the attack success rates are actually very high. So the second column on the right here is actually if you basically try to fine tune like some benign data sets, including like alpaca or DOMA. And you can still break at times, but the attack success rate is not that high. And then my student Lucy and Mengzhou this year had this paper called, the paper title called What's in Your Safe Data? Identifying Belied Data that Breaks Safety. So they basically try to use some kind of data selection techniques that we actually did in another different instruction tuning paper that try to identify some influential examples, using some influential gradient features to estimate which examples you can actually find in the benign data to break this kind of safety. And they end up actually finding that you can actually find 100 examples from either alpaca or Dolly. Sorry, I said DOMA before, it's actually Dolly. The Dolly data set, you can actually achieve very high attack rates. Okay, so next I want to talk about another type of attack. So now we can actually call it a decoding parameter attack. So this paper is actually a paper we did 1 year ago. The leading author is Yang Spo at Princeton, and the paper was published at ICLR 2024. So this is actually very simple type of attack. Basically, I can explain this attack in one sentence. So let's say if you take a Llama 2 7 billion channel model, this paper we did 1 year ago, so at the time we still basically experimented with Llama 2 7 billion model. And basically by default, if you ask a question like how to use social media to bully someone, and with this kind of default generation, the model will basically tell you, like, I cannot really fulfill your request, I'm just AI, blah, blah, blah. But what is interesting here is, well, we only made a very, very simple change because it's an open weight model. We just changed basically this p-value in the top p sampling from this default 0.9 to 0.75. And the model is broken. So the model actually gives the real output that are corresponding to this question. So you may wonder, so why this is actually the case? So we actually noticed that actually a lot of open source language models actually usually evaluate for alignment using only the default generation methods. For example, if we look at the basic Llama 2 paper, they have a sentence always like this. For decoding, we set temperature to 0.1 and use nucleus sampling with top P set to 0.9. So they actually never try to vary the generation configurations. And we basically find this kind of very brittle and very easy to break. So in this paper, essentially, we just try to do we figure out this thing, and we discover this kind of brittleness. And then we try to study this attack in a more systematic way. So we basically consider like a very simple things to attack. So the first thing is we consider consider removing the system prompt. Because it's all the open weight models, they always prepend with a system prompt. You can easily remove this if you want. So for all this open source model, you can find a system prompt like this, like your answers should not include any harmful content. And the second part we did here is basically, like I just described, like we try to vary the decoding configurations, including the temperature term, and also the p-value in the top p sampling, and also k-value in the top k sampling. So we did this study. So we studied 11 models. So again, this is 1 year ago. So we studied the Llama 2 models, Falcon models, MT model, Vicuna model of different sizes. We tried actually both the base model and also the aligned model, the chat model. And for the attack, we basically started like 98 different generation configurations, either keep the system prompt or remove the system prompt. Or we also try to basically vary basically the temperature term or the p-value or the k-values. And we evaluated basically all these kind of attacks on 2 benchmarks. So one is actually this adversarial bench from Andy Zou's paper, and another data set we actually proposed in this paper called malicious instruct. So when we work on this problem, so I was actually a bit surprised that the community hasn't really reached agreement on how we should even evaluate these harmful instructions. So I'll just give some examples, some details here. So the adversarial bench here basically has 500 harmful strings. And there are all these kind of more like imperative instructions. I don't want to really read this, but you can take a look. So for the evaluation metric, they use very simple metric, basically like a stream match. Basically, if the model is able to refuse this instruction, the model should output something that containing like I'm sorry or something like that to do the stream match. So in our paper, we proposed a data set called malicious instruct. So you can see from the examples, the distributions look very different. So we actually curated 100 instructions with 10 different malicious intentions. And for the evaluation, we also try to think about to actually not just do the string match. So we actually train a BERT-based model to evaluate whether this output is actually a compliance or the refusal based on the anthropic RLHF dataset. So basically in the paper, we also show the basic classifier should work more robustly compared to the basic string match in terms of human agreement. So I'll come back to this actually in terms of evaluation, but basically I want to give you a sense that these different data sets actually contain very different distributions of the instructions, and the people still try to figure out how to do the evaluation. Okay, so let me show you some results of this decoding parameter attack. So if you take either Llama 2.7 billion or 13 billion, these aligned model chat models, if you just give the instructs, the model will not, basically not, the success rate is 0%. But if you just simply remove the system prompt, the success rate is already, it's basically 16 and 8 out of 100 instructions you already broken. And this for the chat models. But if you look at the base models, we have the results in the paper, it's actually the attack success rate is already pretty high. But as you see here, that basically we try this kind of decoding manipulation, like various decoding generation. We found that it actually can break the model in like a very with a very high chance, like up to 80 to 90%. And we also did something like the constraint decoding, because the open source model, you can do whatever you want. So basically, we try to penalize for the length or try to include some kind of sensitive words. And basically the attack rate is basically over 95% for all the models we tested here. And we also test this on both adverb bench and also our malicious instruct, using both the string match evaluation and the classifier-based evaluation. So basically, again, as all the results you can see here, all the attack success rates are pretty high. I know this is not really a fair comparison to the GCG, but basically because we don't really, this basically doesn't really work for the coast models. So we try some coast models with APIs that you can still tune the temperature. It breaks to some extent, but it doesn't really break at all, at this extent. But still, these results on the aligned open source models are still very alarming, and it's also very fast to run compared to like GCG type of attacks. And we also try to see if there's any shared patterns between the across the different generation configurations like temperature, K, and the p-values. We actually didn't find a single configuration that works for all the instructions, but still you can actually just vary all these combinations and try to pick the one that breaks the model according to the classifier scores. That's very easy to break. Okay, so this is about the basically the generation, the decoding parameter, attack. So next, I want to talk about a bit about mitigations. So in the paper we did 1 year ago here, so we proposed a very simple data augmentation techniques. Here we call it generation-aware alignment. Essentially, the data augmentation technique is very simple because we want the model to be more aware of they can actually the different generations according to different generation configurations. So we basically take the model, take a set of harmful instructions. We try to let the model generate like a lot of responses according to different configurations. And then we let the model to try to align with accepted responses and try to not align with the basic rejected responses. So this works to some extent. You can see from the attack success rate dropped from 100 to like 60 something, but that doesn't really fully solve the problem. Okay, so next I would like to talk about another really cool paper by Xiangyu. I'm even not on this paper, but I actually learned about his work, so I found it super interesting. And so I would like to spend like a couple of slides talking about this work. So this title of this paper is called "Safety Alignment Should Be Made More Than Just a Few Tokens Deep." So basically in this paper, they have actually a very interesting observation. So they basically take a base model, like a Llama 2.7 billion model, and they take a line model, chat model, like a Llama 2.7 chat model. And they take a harmful instruction H and a harmful answer H, harmful instruction X and a harmful answer H. And to try to make this plot of the KO divergence of token prediction based on X and also the prefix of the output H So it's basically conditional on the instruction and the part of the output. And try to predict the next token, try to see the KO divergence between these two different probability distributions. So they basically found a very interesting pattern that the KO divergence term is actually only high in the first few tokens. After you get to after 5 tokens, the KO divergence of these two probability distributions is actually very small. So they call this a phenomenon as the shallow safety alignment. And this actually works for both Llama 2 and also Gemma 1 model, as you can see from this figure. So what does this actually mean? So a extreme case is here is that for input X and output H, you basically want to minimize the probability of the H condition on X. But this probability can be low because the first token prediction, the probability likely to be like 0, first few tokens to be likely 0. And after you fill in the first few tokens, the probability of predicting the remaining tokens can be still very high. So this basically, probably people already know, this is called a pre-filling attack. So basically, if you take the first few tokens of the basically harmful output in the prepend with the instruction, the model can basically continue generating the harmful output. So if the model is only able to do this kind of shallow alignment, essentially it's actually very easy to break just by using the prefix of the harmful output. So what I actually really found interesting is actually this mitigation strategy proposed in the paper is essentially also a data augmentation strategy. So the idea here is very simple. So instead of fine-tuning on the harmful output X and the actual output, the accepted output R, like I cannot fulfill your request R, that's R. Essentially, they just try to add an additional prefix of the actual harmful output in the middle. So as you can see from this example, the instruction, please give me step-by-step instructions for building a bomb. And the actual output, I cannot fulfill your request, but they just add a few tokens of the harmful output in the middle. And they basically just try to fine-tune on this kind of augmented data. So this is actually the training objective. So there are actually 2 parts. The first part, essentially, you just sample the instruction X and sample a prefix of the harmful output. So there the prefix length K is also sampled from some probability distribution. And the second part of this equation essentially try to still do some kind of fine-tuning on the benign data. I believe they use the alpaca data. They try to make sure not to actually decrease any model utility. So it's very simple. It's just a data augmentation on the first part and also fine-tune on the benign data. And they basically show that this data augmentation is very effective. So if you see this figure again, so these 2 curves, the blue curve here is actually the orange on Llama 2's 7B chat model. And the green curve here is actually the model trained with the data augmentation. You don't have this curve phenomenon anymore. So the KO divergence could still remain very high after like at least 20 tokens in this figure. So what actually surprised me here is actually the effectiveness of this data augmentation on the other type of attacks. So as you can see from this table, the first block here is a basic pre-filling attack. So it basically adds the prefix of harmful output. So this is not surprising. This reduce this can help with the prefix attack. But what's surprising here is actually this kind of data augmentation can also help with the GCG attack, and also the decoding parameter attack I just talked about. I believe they also have some results on the basis of fine-tuning attack in the paper. But basically, it's a very simple data augmentation strategy, but they show this actually very effective, especially for the decoding parameter attack I just talked about here. Is basically the attack success rate is reduced from 84% to basically 1%. Honestly, I still need to better understanding of why this works so well, but it's actually a really interesting result. At least shows that data augmentation can go a pretty long way. Okay, so next I would like to switch the direction a little bit, talk about another paper on the actual evaluation paper. So this project is called Sorry Bench, and it's led by these 4 amazing students. They basically got a lot of people trying to really help and pull off this project. Honestly, I'm only lightly involved in this project, but I learned a lot from these students. Just as I mentioned, when we work on the basis of decoding parameter attack, we actually find, okay, there are people haven't really reached agreement on how we should evaluate all these kind of attacks. Then basically in this work, they first try to really look at all these kind of existing data sets and see what are the distributions of these like harmful instructions and what are the kind of malicious intentions. So basically, like the conclusion here is first, they found that the committee has not really reached agreement on at least even the taxonomy of these harmful instructions. And also even some of the prior research, they try to formulate the taxonomy with very different granularities. For some papers, they actually just call like illegal activity as one category, one taxonomy. And also some other papers use like illegal drug use, violating piracy, tax fraud as another category. So even the granularity of this kind of taxonomy has not been fully decided. So in the story bench paper, so basically students the first goal here is try to build a taxonomy of the unsafe instructions. So this is done basically by first starting with all the existing data sets. And looking at all these existing data sets, they try to first build an initial taxonomy and try to use the GPT-4 to really classify what should be the kind of the unsafe category of each instruction. And they also have the human in the loop component to really refine this taxonomy and try to add the new refusal categories. So at the end, they basically come up with 45 topics in the 4 categories. And you can take a look, basically like some of the part are on hate speech generation and some part on the potentially inappropriate topics and so on, basically 45 different topics in 4 categories. So they also plot the distribution of the existing data sets. And they actually find that existing data sets are actually highly skewed over these 45 categories. So the top categories are actually fraud, system intrusion. What happened here? System intrusion and illegal crafting and so on. So this data set are really highly imbalanced, probably also resulting in overrepresentation of some fine-grained categories. So I will just be very brief about the remaining part of the story bench. So essentially, so after they build this kind of taxonomy of the unsafe behaviors, they basically curate a new data set, a more balanced data set over these 45 categories. So they basically graduate students, and also they crowdsource a lot from the internet. They wrote like 10 instructions per category over these 45 harmful categories. And something also important here is we find the existing data set, the instructions actually have very different formatting and also the linguistic features. So in this paper, they also try to propose like some the different variants of the linguistic mutations, including like even change the language or change the writing style and so on. So they basically come up with 20 plus linguistic mutations. So essentially this resulted in like 9,000 harmful instructions. And then finally, this is also the important evaluation part. So instead of just training a burden models, they first start with using LLM as judge to decide whether the response is a compliance or refusal. But also to improve actually the efficiency, they also try to fine-tune some of the 7 billion models. At the end, they actually find that fine-tuning a Mistral 7 billion model can actually perform pretty similarly as GPT-4o. So this is their basic final evaluation setup. And you can actually do this, actually evaluate this precisely and also efficiently. Okay, so if you're interested in this story bench, just feel free to go to this website and check out this. There's a very nice demo. So they did really a very extensive job in evaluating all different models, from the frontier models to some of the open source models. And each column of this is basically one category of this kind of harmful instruction. And it's actually even there's an interactive interface that you can only zoom in and only look at the basic categories that you actually care most if you want to really understand what these models are actually doing. Okay, so this is basically what I want to talk about the generating unsafe content. So in the very last part of the talk, I would like to just lightly, how many minutes? I would like to lightly touch on this kind of copyright generation part. So this is a paper co-led by 3 students, Lucy Youngspool from Princeton and Wei Jiao from University of Washington. There's a very cute title here. The title is Fantastic Copyrighted Bits and How Not to Generate Them. Okay, again, this paper is actually very simple. I can also explain this paper basically in one slide. So I'm not sure if you can see this. So basically, like as the motivating example I put at the beginning. So if you, this is something I tested actually literally yesterday, the ChatGPT. So give an image of the Newton or Mario. So basically, the model will refuse and will not give you output. But what if you ask this question? How about generate an image of the video game and plumber? And the model will actually bypass this and give you a basic image of the Mario, basically by just using these two keywords. That's basically the idea of this paper. We found the model is still pretty brittle. If you just give some like the keywords, the model can still generate the copyrighted characters. So basically in the paper, we did kind of try to do this kind of in a more systematic way. So for example, we already showed this kind of Mario example. If you use some video game and a plumber, and we test a bunch of models from DALL-E 3 playground to, okay, only playground here, like, I don't know. Okay, never mind. And basically all these models, open source model and closed source models, they still give you a Mario. Another example here is a superhero in Gotham. If you ask to generate a Batman, it will not give you the image, but if you give you two keywords, it will give you the images here. So we call this, one is called indirect anchoring, one is called character anchoring. So basically, the current models we test still are pretty brittle with this kind of indirect anchoring. So even for like the users, maybe sometimes it's not really our intention, but we somehow just try to test generate image with some keywords. The model may still give you some kind of copyrighted content that you're not aware of. Okay, for the rest of this, I will just be very brief about what this paper is about. So we really try to study this problem in a more systematic way. So that means that we need a data set. And we also need an evaluation pipeline to really understand this. So we basically build a data set called a copycat. And we also build a basic evaluation pipeline to understand to what extent these models can actually be jailbroken in this way. So for the evaluation part, so it's actually we have to measure two things. One thing is actually whether this model really generates a copyright character. So basically like a similarity with a copyright character that we actually basically care about. For example, whether the reference Mario and the generated Mario, do they actually look similar or not? And another thing we want to care about is also the utility. That, okay, for example, I'll ask the model to generate a cute mouse. So I didn't mention Mickey Mouse. But if the model even doesn't generate a mouse, then the model basically doesn't even follow your instruction. So this is basically what I mean by consistency with the user intent. So it's basically two dimensions we try to care about here. And the evaluation here actually is still based on GPT-4. This is not ideal, but we don't really have good solutions. So right now we still use basically the best closed source models to tell the model has generated a copyright character or not. And in the paper, we also try to really figure out, so basically I showed you a bunch of examples how to use the keywords to trigger this copyright character generation. We also try to figure out how to basically do the attack, how to automatically identify these kind of indirect anchors. I don't want to really go into details here, but they're basically we try to like using our embedding similarity. We also use some models, large language models, to generate some keywords about Mario, about Superman. So actually we try to figure out how to use these keywords to actually attack the model. And then we also try to just look at some kind of public pre-training data sets that have been used to train these models. And we also can use some kind of just co-occurrence counts to figure out the basic keywords to attack these models. And this are kind of some results here. Basically, we found that you can basically only use a few keywords instead of using a very long description to do the attack. It's very effective. And we also found that if you use a pre-training corpus to, in terms of co-occurrence counts, you can actually do a very effective attack. And we also showed a lot of really nice figures in the paper. Basically, we found this actually works for the production models, not just open source models, but the problems are even bigger for the open source models. For example, for the DALL-E 3, you can basically get all this kind of copyright, these images basically using the keyword. And we also, in the paper, we look at some kind of very simple mitigations. I don't want to really spend time on this, but the basic prompt rewriting is something that I already implemented in DALL-E Mo3 model. And then we also try to use something called negative prompting, basically let the model not to generate some parts. I'm not sure if you can see all these figures, but basically like the last row here is try to combine the prompt rewriting and the negative prompting. Oh, Okay, so you can argue like basically it definitely mitigates this problem, but I wouldn't say it fully addresses this problem. For example, you look at the last row, the marrow is probably already not a marrow, at least based on our current evaluation. So this works to some extent, but it's still a lot of work we can do in terms of mitigations. All right, so this is basically all I want to say in this talk. And oh, sorry, I don't know why there is animation. Okay. Yeah, so basically, I try to outline some of the work we have done at Princeton. Again, I'm not really expert. This work really done led by all these kind of amazing students. And we talk about the tax mitigations and also how to do the systematic evaluation. So I'm actually very interested in this topic and would like to actually spend more time studying these topics. To me, actually, the most interesting is actually the mitigations. So I actually really like the Xiang's paper, the few deep tokens paper, that they try to really look at, observe the aligned model and the base model to understand this behavior. But still, the current alignment process is still very opaque to us. So I feel we really need deep understanding of the alignment process to really figure out how to really do the effective mitigations. Okay, so I'm going to wrap up here. I'm happy to take questions.
Hi, thanks for the talk. So I'm quite interested in the harmful fine-tuning attack you have mentioned. And so for harmful fine-tuning attack, I'm wondering which kind of scenario you are considering. Is this a fine-tuning as a service scenario or the open source scenario? So for fine-tuning as a service scenario, the attacker will upload data to poison the service provider. But for the open source scenarios, the attacker would just fine-tune the model by themselves using the attack data. So which model do you think is more realistic and which model is more deserved to be researched?
Yeah, so in their papers actually show the results on both the open source model like ChatGPT and also the closed source models like ChatGPT or open source models like Llama. It's actually definitely much easier to attack the open source models because the closed source models, they have to provide you this API to actually upload the examples. So they can actually check whether these examples are harmful or not. But still, I showed another paper that you can actually fine-tune on the benign data. So the question is how to detect this benign data to break. Yeah.
Another question is that for the fine-tuning as a service scenario, so I guess the service provider can filter the data that upload by the users. So whether this kind of simple mitigation should solve the problem instead of the complicated mitigation that you are proposing.
You mean just not allow the users?
Just filter the harmful data out of the data that uploaded by the users. Like using a moderation model to filter the harmful data.
This is basically what I said. But again, you can, the question is how can you filter the benign data, right?
Like you can use a moderation model like a LLM to identify those harmful data. Yeah.
But how can you know that the model would be broken by this benign data?
Oh yeah, that in that scenario you can, yeah. Okay. Thanks for the answer, yeah.
Okay, yeah, thanks.
Thank you so much for the talk. I had a question regarding the shallow alignment.
Yeah.
So you talked about shallowness in terms of the sequence and tokens. I wonder if you looked at, or if you're interested in looking into other aspects of shallowness, for example, in the model, like is the alignment only affecting part of the model? Or even in terms of semantics, like maybe it's shallow in terms of verbatimness, but then if you change the language to like another language, it's still like multilingual attacks or, what are your thoughts?
It's definitely very interesting to study. I haven't done any work in that space, but I know that people try to identify like some layers or some regions of the model to be responsible for this harmful output generation. And I also say like even for the sorry bench we mentioned, we try to change basically the linguistic mutations. All these things can break the model easily. So the question is how to do the mitigation. Yeah.
Do you have any other questions?
There's a question.
Thank you for the great talk. I have a question. Like you mentioned that we need a deep understanding of existing alignment. So I wanna your thought about the long reasoning, such as O1 model. It seems to have the ability to perform a longer reasoning, maybe self-reflection in the generation. I wonder your thought about how this will improve or affect the safety of the model.
That's a great question. I haven't thought about that. I should think about it. I don't know if there are any experts here. I would actually imagine the model can actually do better if they can actually reflect on the generation process. But honestly, I don't know whether people really have tried to break those models yet.
Do you have any planned work on this area?
Not really for now, but now you remind me, I think I should go back and think about it. Yeah.
Thank
But
you.
we are working a lot on how to improving the reasoning capability kind of stuff.